Hello, I'm Mr. Troha, and we're going to have some astronomy notes on cosmology and the introduction to that. So this is all about the beginnings of the universe and information about the universe as a whole. So the universe, if you think about it, if you were making a universe, you could either create a finite universe or an infinite universe. And a finite universe is one where the gravity, objects have gravity and they will affect each other no matter if they're really far away. So eventually all those objects would come together into one point. Now if you had an infinite universe, that would mean an infinite number of stars and galaxies, and they would be all at every single point all the way around as far as you could look. And if that was the case, we would have light coming to us from all points. And so you would see kind of a glow. This is Olber's paradox. Is that if we had this, we would see this glow in the universe, which we don't. So an important thing is about when we use the word universe, so there's universe and then there's the observable universe. The observable universe is as far out as we can get light or we can receive light. So this is about 13.7 billion light years away. And so that's as far as we can see. Now, that doesn't mean that that's as far as the universe can go. It is seemingly likely that it is much, much further away than we have the ability to see. Now, the cosmological constant is interesting. Einstein was developing and thinking a lot about the universe, and he ran into this problem about the finite universe being one where everything would collapse in on itself. So in an effort to make sure that that didn't happen in his equations and things, he formed what was called the cosmological constant. And it was this term in his formula that was basically an anti-gravity. And he actually thought it was, he just made it up. And wasn't very impressed with himself, but that was what had to happen. So at the time, Vestos Silfer was busy measuring the velocities of galaxies and checking on the redshift and blue shift of those. And what he found out was that based on the redshift of the galaxies, remember that as relative velocities, as things are moving farther away from us, then the light is shifted towards the red of the spectrum, and if it's moving towards us, it's shifted towards the blue side of the spectrum. What he found out is that the vast majority of galaxies were all moving away from us. Now, Edwin Hubble took this information of the velocities that Silfer had discovered, and then used a method called parallax to determine the approximate distances of these galaxies. Put it on a graph, distance versus, or velocity versus distance, and it ended up being a linear fit. So we have this velocity is capital H, which is Hubble's constant, times the distance. Now notice all these data points don't fit right nicely on the line. That's because there is definitely some error, some random velocity between what these galaxies are moving on. So it's not perfect, but there is a definite trend that as the galaxies are farther and farther away from us, they are moving faster. That is Hubble's law. Now, the cosmological principle, this is this idea that if we are not in the center of our solar system, we're not in the center of our galaxy, we aren't in the center of our group of galaxies even, so it's pretty likely that we are not the center of the universe, as much as some of your friends or whatever might think that they are the center, they are not the center, and we are not the center of the universe. But interestingly, the cosmological principle is based on all of our evidence is that the universe is homogeneous. It is the same. It is smooth throughout in every direction, and it is also isotropic. So there's no specific direction that it's going. Everything looks the same all around. And so interestingly, though, galaxies are all moving away from us. That would seem like we're the center. However, I want to give you an analogy. Imagine if all the galaxies were placed on the surface of a balloon. So they're all on the surface of the balloon that can stretch And as you fill the balloon up, all the galaxies on the outside surface, and you can even, if you have a balloon, I wish I had one here, I'd have one in class, you can write on it and blow it up, and you'd see that everything stretches apart from each other from all sides. And so what's actually happening is all these galaxies, every single one of them, would be moving apart from each other. But not because they're moving, but because the space between them is stretching. In fact, they're stretching everywhere. So we are not actually moving away from the galaxies. The space between us is increasing. Now, going back to Einstein, remember he said that he had made up this cosmological constant. At the time, he said it was his greatest blunder. But really, he just didn't live long enough to actually find out that he was correct. So Hubble's law, it solves both this problem of the collapsing caused by a finite universe, as well as Olber's paradox, which was the infinite universe. Now, as to the age of the universe, it also implies that the universe started, if everything's expanding away, it started from this initial spot. And these galaxies must have flown apart from there. Now, that implies that there is some age to the universe. So we'd have to go back and say, well, how fast are these things expanding away? And how is gravity actually affecting it? Is it slowing down or not? What's the density of the universe? So I want to talk, there's other videos on this, and so I'm not going to go through these specifically, but I did want to have it in this slideshow so you could pause it or look at it or whatever. But, everything started, and we know information based on a Hadron Collider and different things like that we know things about what happened very early on in the universe. We can recreate those. But some amazing things I just wanted to point out that you start off 10 to the negative 36. We're talking from 0.0000, 35 zeros, and then a 1. That's when the gravitational force starts. Then we get the strong nuclear force and the electroweak force. And so that starts to form then quarks, and we get the weak nuclear force. At 1 second, and along this timeline, we now are able to form neutrons, protons, and electrons. And all the neutrons, protons, and electrons were formed within the first 4 seconds of our universe. So we go through, and now we have things, it's all just radiation, and these particles aren't able to combine together. Energy and matter are all very similar to each other, but over time they start to spread out. And as they spread out, because again, the universe is expanding, the space between things is growing, and as that happens, it starts to cool off. And it cools down, and eventually cools down to so that it can form hydrogen. So now we have this. These photons are flying around, but they're being starting to get captured by these different particles, and so we're able to get hydrogen and potentially helium in some of these. Kind of. And so, but there isn't any light yet. We don't have fusion. We don't have a collection of stars at this point. So moving forward 100 million years, we now are getting the first stars, and so now we have light and visible light as it is. There's always light from different kinds of electromagnetic spectrum radiation, but now we're getting visible light. So just an interesting little graph. We have radiation is dominating. We do have some matter, but it isn't until later that we eventually get this first stars and galaxies forming. That's 100 million years down the road. So all of this was happening, and here we are, right there now. All right, now the shape of our universe. Interestingly, the universe is, as I said, it looks the same in all directions. It's isotropic. It's also homogeneous. It's uniform throughout. Those are the things that created this cosmological principle. Now, this image that we're looking at right here This is a representation of the cosmic microwave background radiation, CMB or CMBR. And that's this evidence that we have that is uniform. This is evidence that we have from early stages in the universe where these photons were all flying around, but these are from ones that are not absorbed. So this is happening. We see this all over the universe. So if but as far as the shape of this universe, we don't have a center. If we don't have an edge, what is the shape that we're talking about? So Hubble also then points to kind of three possible shapes or things about the universe. It could either expand forever, meaning if there's no bound at all, completely infinite. We could have the gravity could start to pull it back together, and so at some point there's going to be a limit, and it'll come back together. So that would be a closed universe. Um, or you could have something in the middle, which is between open and closed, marginally bound, or a flat universe, which is actually what we have. Interestingly, we consider our universe to be flat. There's one of our videos by Physics Girl. You can look at that, and she explains and goes into why those things happen. So a couple misconceptions. The Big Bang is not a big explosion. It's not. It's more like that idea of the balloon being blown up and stretched in all directions. So imagine if you're sitting in your house and you have eating dinner and you guys are all around the table, and then instantly everything expanded to a billion times the size. You wouldn't be able to see anybody anymore, right? They'd be all so far away from you. But that's what happened. It just everything just got expanded, the space between everything. So that is a Big Bang. It's not so much of an explosion, more like a big, huge stretch of space. Also, there's no center of the universe where this happened. It didn't start at one specific point, just everything expanded all at the same time. So how do we know these things? A couple of things. Hubble Space Telescope, which is able to look deep into space. It actually has received light as far as we can actually receive light, so 13.7 billion light years away. It actually has the ability to see farther than that, but that's what we're looking at. So our observable universe is 10 to 15 billion light years. And remember, a light year, if it's 13.7 billion light years away, it took 13.7 billion years to get to us. So that's how old that light is. Also, galaxies are all moving away from us, the vast majority. Right? The CMBR, it tells us about what things looked like prior to having all this matter and all these stars. So these photons that are now running into us, we are seeing what they looked like, and based on evidence of how old they are, we can tell what they would have been like then, and now they're down to their microwaves. So radioactive decay, if you look at some of the particles and things, it gives us a good idea that things did actually happen 13.7 billion years ago is a good estimate. And we are using particle accelerators, so that gives us some idea of what's happening back in the very early stages. All right, so there's another picture of the cosmic background radiation there, and just a little timeline down the bottom. And this is just a little bit of information about it. Obviously, we didn't talk about things like dark energy and dark matter or a lot of the newer ideas. I really hope that this is something that interests you and you get an opportunity to look out some more information on cosmology.